Great. Welcome everyone for today's quantum space-time seminar. We are very happy to have Akshay Yelleshpur from Oxford, and he's going to tell us about scattering amplitudes and holography. Over to you, Akshay.
Okay, so thank you. Yeah, thank you. I'm very excited to give this seminar here. So this will be based on a series of papers that I've written over the past 2 years or so, and also on some upcoming work with my collaborators at Brown. I was at Brown until September, and I've moved to Oxford recently. So the main theme of the talk is about flat space holography and scattering amplitude. So I will be focusing essentially on massless particles in asymptotically flat space-time. And the main theme that I want to convey is that amplitudes are at the heart of any holographic program. The S matrix is a natural candidate for a holographic description. Essentially, you're scattering states which are on the boundary, this is the natural cousin to ADS boundary correlators or the wave function of the universe in de Sitter. But one thing unusual about the S matrix is that we already have lots of different ways of computing scattering amplitudes. Many of these don't even make a reference to the Lagrangian or path integrals or field theory. So it's very tantalizing that there's another completely new formalism by which you could compute these in principle as the correlation functions in some putative boundary theory. But the situation at the moment is that there is no first principles definition of what this boundary theory should be, except in some very toy models that have been that people in the Twister community have been working on. So the main goal of this talk would be to tell you what we can learn about this boundary theory from what we already know about scattering amplitudes. So before I actually get into the heart of the talk, I want to spend some time in making this slightly more rigorous. So the usual way that we think about scattering amplitudes, or at least the textbook way of thinking about scattering amplitudes, is that you start with a time-ordered correlation function. And then when the particles go on shell, this correlation functions develops poles. Since I'm only focusing on massless particles, these poles are just as p squared going to 0. And in the traditional framework, you strip off these poles, and what is left is the scattering amplitude. So in practice, when you're computing Feynman diagrams, you don't attach propagators to the external legs. And the way this makes a reference to the boundary is that when you're doing the integral over space-time to convert the position space correlation function into momentum space, these poles actually arise from the regions of space-time integration, which involve the far distant past and the distant future. But you could ask whether there is a way of reformulating this process which makes it closer to holography. And in particular, you could try to associate the in and out states, which are these on-shell external states, to boundary values of operators in the bulk. And this can actually be done. So the question here is, can we interpret the in and out states as arising from boundary values of operators? Of course, you first have to specify what boundary. And to do this, a useful way is to write down Bondi coordinates. And since we're concerned with massless particles here, the correct boundary is either future or past null infinity. And so in these coordinates, this is achieved by taking r to infinity and holding u fixed. So if I start off with a field in the bulk, this is a solution to for the example, I'm considering a scalar field. So it's a solution to the massless Klein-Gordon equation. And I can expand this in creation annihilation operators. So this satisfies the Heisenberg equations of motion. And now I can take r to infinity and see what happens to this field configuration. And it turns out that I can actually do 3 of these integrals using a saddle point approximation. And the field configuration actually looks like what I've shown here. So omega here is actually associated to the energy of the particle. So the momentum, I have parameterized the momentum p of the particle like so, as I've given at the bottom of the slide. So omega is its energy, epsilon tells you whether it's incoming or outgoing, and W and W bar pick out the direction of the momentum vector. Now you'll notice that in the field configuration, the W and W bar make no appearance. And this is because in this asymptotic limit, the direction of the momentum has become identified with a point on the celestial sphere. So you only see Z, Z bar appearing here, but you do not see a W, but you see the energy appearing here. So what this is telling you is that in this limit, there is an identification, there is an asymptotic identification with the momentum direction and a point on the celestial sphere. There's already two of these coordinates of the momentum are already linked to space-time boundary. The only coordinate you're left with is omega, which a priori has nothing to do with the space-time boundary. But you can see that if I take this field operator and act it on the vacuum, what I create is, of course, not a state of definite energy, but it creates a state localized at a point U on the boundary. And it is smeared over all energies. This is the integral over omega. But I can actually invert the Fourier transform and create a state with definite energy. And now this has the interpretation. This is an in or out state. And this has the interpretation of being smeared all along the null boundary of Minkowski spacetime. So in this is the way in which you can connect in and out states to boundary values of an operator in the bulk. And so this is the main reason why scattering amplitudes are at the heart of holographic programs. And so what I want to point out here is that traditionally, scattering amplitudes are written in a momentum space. They're written in a basis of momentum eigenstates. And you label the states by the energy omega and two coordinates on the celestial sphere, Z and Z bar. But there are many other bases in which you can choose to write the S matrix. So one of them is the position basis that you already saw here, in which you keep the Z and Z bar, but you exchange omega for the null coordinate U on the future or past null boundary. And this matrix and the S matrix in position space, there is a conjecture, there's a holographic conjecture for this, and this is called Carolian holography. And the main conjecture is that these S matrix elements are essentially correlators in these Carolian conformal field theories. There's another basis in which you can write down the S matrix, and these are eigenstates of boost. These states do not have definite energy, but they have definite Rindler energies or boost weights. And this is delta. And you can get from the momentum eigenstate to a boost eigenstate by doing a Mellin transform. And this exchanges omega for the label delta. And in this state, and in this basis, the conjecture is that these celestial amplitudes, which are essentially Mellin transforms of scattering amplitudes, they are correlation functions in the 2D conformal field theory. And this goes under the name of celestial holography. Essentially, the two holographic conjectures are related to each other because they're essentially the same object, but you're viewing them in different bases. And it has been shown that you can actually go from celestial correlators to Carolian correlators and vice versa. You might think that the celestial correlators are being in a two-dimensional conformal field theory, this is somehow at odds with the three-dimensional field theory of Carolian holography. But you can think of delta, the conformal dimension, as being as mode expanding along the U direction. And this is indeed the case because the conformal dimensions in celestial holography are continuous variables. So even though it looks like you've lost a dimension, they essentially, both of these correlators essentially contain the same amount of information. In this talk, I will just be focusing on celestial holography. I won't have anything to say about Carolian. So this is the outline of the talk. I will first tell you about the symmetries of the celestial conformal field theory. And then I will describe some generic features of the correlators in this theory. And after that, I will essentially focus on OPEs in this theory and tell you about constraints OPE associativity places on scattering amplitudes and vice versa. And I will end with a curious role played by supersymmetry in this whole story. Okay, so before I start, are there any questions about anything I said so far?
Akshay, I've got a question. Thanks a lot for this beautiful summary, which is already very helpful for me. I'm out of the field. Is there any sense in which the boundary theory, whether we think of it in terms of Tyrolean or in terms of celestial holography, that the boundary theory is local? It has some kind of local notion of energy momentum tensor or something in any of these descriptions? Is there any?
I will answer this for the celestial because I don't know too much about Tyrolean yet, but there's definitely a stress energy tensor for the celestial conformal field theory, and I will tell you a bit more about it maybe in 2 slides from now.
Okay.
But there are also non-local operators which enter the game, like there are these light ray operators which appear to be generic in these celestial conformal field theories. So,
okay.
Yeah.
Thank you.
Akshay,
okay. Yes.
Sorry, one more question, please. Suppose we were to regulate your infinity, so you weren't quite at infinity. So let me regulate it by making some sort of space-like surface.
Right.
Okay, so that your scries, your light-like things have become some space-like thing, and then this is a little like a pillbox, where we've got a surface at one late future time and another surface at one late past time. One early past time. Okay. Now, if I try to do kind of holography in the sense of action as a function of boundary values in these 2 surfaces, you could imagine a scattering process that happens not in the center of space, but sort of 3/4, meaning a quarter up and 3/4 down, if you know what I mean. Meaning not right in the middle, but nearer the top boundary than the bottom, just in sense of ratios. When that happens, it no longer seems clear to me that your positions of the sphere will be identified with momentum, because you'll be looking at angles of the sphere from the origin of R4, where your scattering will happen from some significantly different place. So it seems to me that when you regulate in this way, this connection between momentum and where you are seems more fuzzy. Is that wrong? I'm sorry for the length of it.
No, I think it's correct, but I don't know. I don't have too much to say about what happens if you actually push the boundary in to space-time a bit more. I don't think it has been looked at in much detail. People have looked at taking the slicing Minkowski in this way and taking the limit in which these slices asymptote to scry, but I don't think people have looked at any finite limits of these. But certainly the correspondence is only the correspondence between points on the celestial sphere and directions of momenta is definitely only asymptotic. It's not for finite distances.
But if for any finite distance it changes a lot, then shouldn't one be worried? Because the scattering could happen anywhere, right? It could happen all over the place. So it seems to me that it could change a lot. Meaning that the difference between infinity and any finite number, however large, might be a lot.
Why can't you move the pillbox so that the new scattering place is the center?
You could, but then that's not then you're not identifying with the angles of your whole sphere.
Yeah, but then you can take an asymptotic limit, and then now you have.
But suppose we just keep something fixed. The scattering happens everywhere.
If it happens everywhere, then yes. But you are saying the scattering process could happen in a region which is becoming asymptotically big.
Could, because it could, your boundary the stuff from here could go and meet there. Sorry, we can talk about this later. I don't know.
Any other questions, or shall I go on?
Sorry, just as a clarification. So, for example, the stuff could come out and smear across this scry minus or whatever, right? So that will now meet each other at any point in the.
It could, or even localized, but localized tuned in a way so that it will meet like 3/4 the way up.
Yeah,
you can easily arrange that.
Yeah, but not just one place, right? Then you could.
Then but you could exactly
multiple places
like
that.
Yeah.
Sorry, Akshay. Yes, please.
No worries. Okay, so yeah, let me first back up and tell you why I'm even calling it a CFT to begin with. So first of all, the definition of these putative correlators is that you take momentum eigenstates and you convert them to eigenstates of boost, and this is done via a Mellin transform. So these celestial correlators or celestial amplitudes are essentially Mellin transforms of the scattering amplitudes in momentum space. And already there's an identification of the Lorentz group in the bulk as the conformal group on the boundary of the of Minkowski. And so the Lorentz group acts as a global conformal group on the celestial sphere. So what this guarantees is that if I perform a Lorentz transformation in the bulk, this acts like a conformal transformation on the correlators. And so this is the statement is that Lorentz covariance in the bulk guarantees global conformal covariance of the of these correlators. So we are somewhat there in justifying why these are called this is a conformal field theory. But of course, this doesn't guarantee local conformal invariance, and that seems to come from a slightly unusual place. And this is the statement that there are soft graviton theorems, soft photon, soft graviton and theorems in the bulk, which scattering amplitudes satisfy. And there are, for the gravitons, there are three universal terms. If you take particle 1 to be soft, that is, I take the energy omega 1 going to 0, there is a leading pole, which is 1 over omega 1. And this is the Weinberg soft factor. But it also turns out that there is a subleading and sub-subleading soft graviton theorem, and these are also universal. When I say universal, what I mean is that the soft factor doesn't actually depend on which particular scattering amplitude I'm considering. So if I'm taking particle 1 soft, the species of particles 2 to n doesn't actually matter. And the soft factor will be the same in all such amplitudes. And there's by now an old statement that these soft theorems can actually be interpreted as word identities on the celestial sphere. Now notice that these soft factors are actually angle dependent. And so what this does is at asymptotic infinity, it enhances the global translations and global rotations to local rotations and translations. So there's actually an infinite number of symmetries already at the leading order. These are called super translations. And so on the celestial sphere, you can, at null infinity, you can translate by angle dependent translations. And there's also similarly rotations. And so what has been shown is that the soft graviton theorem enhances the conformal group to the local conformal group, and you actually get the full Virasoro group. And so this connects with the statement I made about the stress tensor, because the soft graviton theorem actually generates super rotations. The subleading soft graviton mode is actually the stress tensor of the CFT. So what you can actually show is that the subleading soft graviton theorem rewritten in the celestial framework actually gives you the action of the stress tensor on the rest of the particles. And so this is the sense in which the soft graviton mode behaves like a stress tensor of the CFT. Now I should mention a few caveats here. In scattering amplitudes, it's well known that simultaneous soft limits involving particles of opposite helicities are not unique. So this actually depends on the order in which you take the particle soft. So for example, if I take a positive graviton soft and then a negative graviton soft, it's different from the other way of doing it. So when you have gravitons of both helicities, the action of the stress tensor, action of two stress tensors is not well defined, but the stress tensor generates the correct OPEs on all the rest of the on all the hard modes. Okay, so before I will now move on to describing correlation functions in this theory. There are a lot more that can be said about symmetries, but for the purposes of this talk, I think it is sufficient. But before I move on to the correlation functions, are there any questions about what I've said in the past two slides?
Hey, I have a question. Again, I'm really sorry for these remedial questions. Just excuse me. But, presumably the soft theorems are true in any number of dimensions, say at least beyond 2 + 1 or something, right?
Yes.
Is that true? I would think, because, but does that mean you get a local CFT in, say, even in 4 + 1D, etc.? Is that true? I'm just curious. If it's an aside, please forget it, but I'm just curious.
There's definitely, I am not sure about the statement of a local CFT, but there's definitely the super rotation and super translation symmetry exists, but whether it actually turns the global conformal group to a local one, I'm not sure.
Okay. Thank you.
Okay, so let me move on to describing correlation functions in this theory. And what I want to convey here is that these are exotic in nature. And most of this exotic flavor comes from the fact that there is this extra translation symmetry that is imposed on these correlators. This is just the usual translation symmetry of the bulk. This is Poincaré. But from the perspective of a two-dimensional conformal field theory, this is indeed exotic. And this is easy to see because I have written out the momentum here. You can see that this depends on the energy omega. Now, when the way this acts on the Mellin amplitudes is you have to, this omega gets changed to a differential operator. It acts as e to the d by d delta. And what this does is that it shifts the conformal weights of the operators. So the statement, which is as simple as momentum conservation, actually ends up giving you relations between different correlation functions with shifted operator weights. So this is not a constraint you expect to have from the point of view of a two-dimensional CFT. So I will expand on this in the next few slides, but to do that, I need to set up some notation. Because I'm dealing with massless amplitudes, it's convenient to parameterize the momentum in terms of these spinor helicity variables. And for the specific parameterization of the momentum that I have shown here, the spinor helicity variables take this form. I've given lambda, lambda tilde here. And you can just contract them with the Pauli matrix to get the actual momentum. These are just the spinors of the Lorentz group, and I can form Lorentz invariants out of these spinors, which are just the determinants of the lambda or determinants of lambda tilde, and this is related to the dot product of two momenta. And so scattering amplitudes will be functions of these square and angle brackets. So let me start with the simplest case, which is 3-point amplitudes. So already in Minkowski space, 3-particle kinematics is kind of degenerate. So if you want 3 particles to be on shell and to satisfy momentum conservation, the only way you can do this is if you have Z1 equals Z2 equals Z3, where Z are the coordinates here. So what this tells you is that the 3-point amplitudes are functions only of lambda or only of lambda tildes. Or in other words, they're functions only of the Zs or only of the Z bars, but not both. I have shown you here the 3-point amplitude that you get for the case when the sum of the helicities is greater than 0. S1, S2, S3 are the helicities of these massless particles. So in 4 dimensions, all massless particles only have 2 degrees of freedoms, and this is plus S and minus S helicity. And the 3-point amplitudes are completely determined. Once you specify these helicities, they're completely determined by Poincaré symmetry, and they take this form. And so already you can see that momentum conservation tells you Z1 equals Z2 equals Z3 is kind of strange, because if you were to interpret this as a 3-point function of a 2D CFT, which you can do by just Mellin transforming it, it has 2 delta functions, delta of Z12, delta of Z bar 3, which is imposing the constraint given by momentum conservation. Moreover, it has 2 theta functions, which come from the fact that you want only positive energy solutions to momentum conservation. Remember, when you're doing the Mellin transform, you're integrating from 0 to infinity. And the momentum conserving delta function is baked into the integral. But when you solve for it, when you solve for the energies, you also need to demand that these are positive, and so that gives you these constraints. So these are the two key points that I want to highlight, that correlation functions in the CFT are at least the low point correlators are distributional, and they have restricted support on the celestial sphere. What I mean is you cannot choose arbitrary points in the celestial sphere and hope to get a non-zero correlation function. These are non-zero only for specific set of insertions. And this actually continues to higher points. At 4 points, there's a really nice way of seeing this. In momentum space, we know that 2-to-2 scattering at 4 points is completely planar. So it's restricted to a plane. And so you can ask where this plane intersects the celestial sphere, and that intersects on a circle. So already this is telling you that the 4-point correlator of a celestial CFT must be supported only on a circle. And indeed, if you actually go ahead and do the computation, you take a 4-point amplitude and do the Mellin transform, you will see that there is a delta function z minus z bar sitting here. Here z is the cross ratio formed out of the 4 points on the celestial sphere. And this is telling you that only insertions of the 4 operators which lie on the circle are allowed. Now, the specific correlator that I've shown you here is the Mellin transform of the MHV gluon amplitude. The precise form of it doesn't matter. I only want to highlight that indeed it transform like it has the usual conformal factor that you would expect. It has the Zij, the bar ij dependence that you would expect. But in addition to that, it also has there's a delta function restricting the support, and also these theta functions which tell you which channel you're in. And this generalizes to higher points. So first of all, you could try to compute higher point correlators in gravity or in gauge theory, but these have been shown to be extremely complicated hypergeometric functions. Just to give you an idea, these functions are almost as complicated as the functions that you would get when you evaluate multi-loop Feynman integrals. They're the same generic class of functions, but these are just for tree-level scattering amplitudes. The Mellin transforms are that complicated. And this complication comes just because of the singularity structure being encoded in a very non-trivial way. And the generic feature that I mentioned of restricted support continues at the endpoints. The configuration space of endpoints in this celestial CFT is CP1 to the n minus the locus where the cross ratio actually, the n minus 3 cross ratios vanish. Sorry, the imaginary part of the cross ratios vanish. Now, this is very similar to the configuration space you get in string perturbation theory, except that in string perturbation theory, you do not have imaginary part. You just have, take out the points where the cross ratio vanishes. So the number of allowed region grows exponentially with n. And so this is the heart of why it's very hard to actually compute higher point celestial amplitudes, because these are very complicated functions which encode all of these, which encode all the branch cuts and singularities which tell you about all of these regions. But however, we can still learn a lot about the CFT just from the singularity structure of scattering amplitudes. And so in the rest of the talk, I will focus just on OPEs of scattering, OPEs of celestial correlators and what you can say about them from the collinear limits of scattering amplitudes. So that's a change of topic, but before that, are there any questions about this?
Sorry, just to understand the formula. Sorry, Siddharth.
Yes.
Yeah. Yeah. Okay.
Go ahead, Shiv.
Yeah. So just to understand the box formula. So what is the dimensionality of that space? This union. So what does minus mean? Minus removing some space of some lower codimension or the same dimension?
Yes, I'm removing the points in CP1 to the n where this the imaginary part of this cross ratio vanishes.
So if CP1 to the n is 2n dimensional in real dimension?
Yes.
And what is the dimensionality of the space you're removing? I mean, I want to know whether it's more, it's less than 2n.
Oh, I think the dimensionality of this space is exponential with n.
I mean, you're removing some subspace of a 2n dimensional space.
Right.
So are you removing? Sorry, I'm trying to. What I'm trying to get to is the following. In the case of, let's say, the 4-point scattering, you were restricted to some manifold of the naive set of boundary insertions because you had delta 1. So the part that you were removing was the same dimensionality as the space itself, right? So that you were restricting yourself to some lower dimensional surface. Is that the same?
Yes. That's the same here. So you end up with full dimension. You end up removing parts of the CP1 to the n. Yes.
Parts of the CP1 and you're left on a lower dimensional manifold, less than 2n dimension.
Yes.
Okay. And, is that much less than 2n? Is like 2n minus 3 or?
I don't actually remember the counting off the top of my head.
Thank you. Yeah.
Right. But
I just had. Sorry, please go ahead.
That's dimension. What you're removing is a higher codimension, not codimension 0.
It's not codimension 0. Yes.
What you're removing is not codimension 0, right? It's higher codimension.
Yeah, it's not codimension 0.
It's higher codimension then, right? So then what you're left with is a set of full measure.
So could you say that again?
I mean, you are left with a lot of CPN, right? I mean, you are removing some higher codimensional loci in CP1 to the power n. Right? Or
is the space you're left with 2n dimensional or smaller dimension?
Locally, let's say you go to some point. Sorry?
I think it's smaller than. Sorry. At 4 points, it's quite degenerate, so you end up with a lower dimensional space. But I think at higher point, it's still 2n dimensional, but it's not. It's not the full space.
Yeah. Okay. Fine. Thank you. So 5 and higher is different from 3 and 4. That's what you're saying.
Yes. 3 and 4 are quite extremely degenerate, but at higher points, the point is it's a full codimension, but it's still not. You cannot put the points anywhere on the celestial sphere. You have restricted support, but it's not as degenerate as the 3 and 4 point cases.
And physically, this is because scattering with higher points is not restricted to a particular plane.
Yes.
Yeah. If you were in higher dimension, let's say you were in 10 dimensions, then you would have to go up to like 8-point or 9-point scattering in order to go to this generic case. Is that right? Basically, the place where you would saturate the number of planes, the space.
Yes.
Okay, fine. Yeah. Okay, thank
you. Somebody else had a question?
Yeah, I had a small clarification. You had you say you call these correlators and endpoint functions, but they're on shell, right? They respect momentum conservation and so on. So they are really to be thought of more as the analogs of amplitudes rather than correlators. Is that right? Or
well, I'm calling them endpoint functions in the 2-dimensional CFT. So here they're actually correlators. They're not necessarily on shell. I don't. So this is a 2-dimensional Euclidean CFT, so I'm not sure what on shell would mean.
But no, I was thinking of a sense of the bulk. You're not
In the
taking
bulk,
like
yeah, there are definitely scattering amplitudes. They're on shell. All the momenta are null and satisfy momentum conservation. Yes.
right. So if you went, some of these properties of the endpoint functions, the boundary that you're getting are because of that, right? In the sense that if you went off shell in the bulk, you might not end up with distributional endpoint functions and so on. Is that?
Yes, that's true. If you went off shell in the bulk, then you would end up with non-distributional. But I don't know any unique way of going off shell in the bulk. So yeah, it's a bit of an open question as to what the correct object in the bulk would be to extrapolate to the boundary.
Okay, thanks.
I thought it had to do with the translational invariance.
Yes. So there are some ways of doing this. You could break translation invariance by introducing a background.
In the way you are doing it,
cases,
here that, for example, in the 4-point case, you got this circle. That was because the momentum needed to be conserved, right? Not because necessarily because it was some on-shell stuff.
Oh yeah. Okay. So yeah, what I meant was there's I don't know a unique way in which you can go from an amplitude which satisfies momentum conservation to something which doesn't, because once you remove the delta function, you're free to add anything to the amplitude which vanishes on the support of the delta function.
Okay, thank you.
So but there are ways in which there are some natural ways in which you can break translation invariance in the bulk, and people have done this by introducing some backgrounds or some non-trivial backgrounds, and in these cases, for example, the simplest case is by introducing a scalar background, and in these cases the background absorbs the extra momentum, and you're left with a correlator which doesn't necessarily need to satisfy momentum conservation. But I don't know whether there's a general story there at the moment.
Also, the story of this Burns holography of Costello and friends, right?
Mm-hmm.
That's one of the examples of that.
Yes, that's one of the examples. They do have backgrounds, and and so they do get correlation functions which are not distributional.
Okay. Yeah. Thanks.
But there are also some other ways in which you can get correlation functions within this CFT which are non-distributional, and this is if you consider light ray operators instead of these primaries. So the light ray operators are non-local in one of the z bar coordinates, and so if you do enough of these light transforms, you absorb the delta functions and end up with regular CFT 3-point functions. And there's good reason to consider these light ray operators, because once you look at the 4-point amplitude and do a conformal block decomposition, you see that they generically show up in these block decompositions. So the kind of the open question is what is the minimal set of operators that you need to consider in the CFT, and what correlation function should you consider as to be defining the CFT essentially.
So in this light ray operator case, I guess is it correct that what I'm thinking? So I thought the way to get to this 4-point function or correlation function which are not distribution valued is when you transform with some kernel, right? Each coordinate separately. So
Yes.
it's like each leg you transform separately, and that's why you kind of now have a more uniform distribution. Let's say not necessarily some restricted to some sort of subspace.
Yes, exactly. So for example, if you look at the 3-point function, if I smear legs 1 and 2, that's enough to get me something non-distributional. And in the 4-point case, if I smear one of the legs, that's enough to get me something non-distributional.
But that sounds, I mean, that seems a little fake, right? That's like you have a matrix with less, not full rank, but you're doing some transformations and making it look like diagonal has no zeros. I mean, but at the end of the day, your correlation function still has support only on that, right? So I guess I'm asking, doing such transforms, does it, and getting something that looks familiar, is that really telling us something? I mean, can a usual CFT be of this type that it's, if you transform it away, I mean, if you transform the legs in some way, you get some secret structure that is that it's supported only on some slice or something? Sorry, probably
So
my
I guess
answer is not very well phrased.
so. I understand. I understand the concern, but I guess the logic here is that maybe. So first of all, because this is a conjecture, you're Mellin transforming the scattering amplitudes and obtaining correlation functions. The logic here might be maybe these are not the most obvious objects to consider. Maybe there are other objects within the CFT which are more obvious, and in fact, these distributional correlation functions are somehow derived from those. And so I guess if your aim is to look for a top-down construction of a first principles construction of the CFT, then you want something that looks like a normal CFT correlation functions, and then so you hunt for objects that might give you clues. But it's not. So the statement is not that the CFT has a well-defined correlation functions. Is that we are looking for objects that might give us clues as to what might be the correct correlation functions to consider in the CFT.
Yeah, but okay, so just let me just ask one more question. I mean, just continuing on that. So, given that these quote normal looking things would come out of these weird looking things by a transform, do you really have a hope of understanding them as normal things? Because secretly they are not normal things, right? So that's what
it seems very unlikely that it's actually a normal CFT, because there's so much more structure that they need to satisfy. So
okay, yeah, sorry.
Understanding them from a normal CFT perspective is seems hard, but I should point to one example. This is in the case of introducing a scalar background. There are papers by Tom Taylor in which they have managed to reproduce MHV amplitudes as some sector of Liouville theory. MHV gluon amplitudes on a scalar background. So once you introduce the scalar background, they break translation invariance and they look like normal CFT correlation functions. And there is some limit of Liouville theory in which some correlation functions in Liouville theory match onto the MHV amplitudes on a scalar background, but I don't think the analogy extends deeper than that.
Sorry, this is a scalar background that preserves Lorentz transformations.
Yes, it preserves the conformal symmetry.
Therefore, Lorentz transformations, is that right?
Yes.
What kind of scalar backgrounds?
It's a delta function source.
I mean, delta function where?
Sorry?
Delta function at the origin.
Yes.
I see. Thank you. Yeah, okay. Yeah, thank you.
Okay. Shall I go on?
Yes, please.
Okay. So yeah, I will now spend the rest of the talk talking about OPEs and how they're connected to collinear limits of scattering amplitudes. So the connection is fairly obvious. As I already told you, the dot product of two momenta in this parametrization is given by the product of the angle in square brackets. And if you actually evaluate it, you see that it has factors of Zij, Z bar ij. So if you take two operators on the celestial sphere and make them approach each other, you see that the two momenta become collinear. And this is also intuitive from what I told you before about identification of the asymptotic direction of the momentum with the points on the celestial sphere. So in fact, the collinear limits of amplitudes govern the OPEs in this theory. And so we're interested in something a bit more specific. We're interested in these holomorphic OPEs. So these are OPEs in which I take the Z coordinates to approach each other without saying anything about the Z bar coordinates. So let me give you a brief refresher about singular limits of scattering amplitudes. So these collinear limits are well studied. And they're captured by, at least the leading collinear behavior is captured by these universal functions called the splitting functions. So again, when I say they're universal, what I mean is that they do not actually depend on which amplitude I'm looking at. And so these splitting functions get contributions at tree level and at loop level, and I will go into detail about this later on. But the upshot is that the OPE coefficient here is essentially determined directly from the splitting function. So the example that I've shown here is that I'm taking two operators with dimensions delta 1, delta 2, helicities S1 and S2. Their OPE gives me an OPE coefficient, which is determined from the splitting function. And the conformal dimension of the operator, of the resulting operator, is determined from delta 1, delta 2, S1, and S2. And so this is just the leading contribution. The sub-leading contributions are unknown at the moment. So let's look at a simple example. This is at tree level. So at tree level, this is quite simple. If I take the collinear limit of a scattering amplitude, it is completely determined by the 3-point amplitude of the theory. This is because in the collinear limit, the two momenta approach each other, and amplitudes have this property of factorizing on poles. So on the collinear pole in which 1 and 2 approach each other, the amplitude factorizes into a 3-point amplitude times an n-1 point amplitude. And so the OPE is essentially determined, or the OPE coefficient is entirely fixed by the 3-point amplitude. So you can do this for the simple case of Einstein gravity. So I consider the usual, if I consider the OPE of two positive helicity gravitons, this is determined by the 3-point amplitude in Einstein gravity. This is the usual amplitude written in spinor helicity notation. And if you actually work it out, the OPE you get is of this form. So kappa 2 minus 2 here is nothing but the usual, is related to the usual Newton's constant. And so you get a beta function, which is essentially the OPE coefficient. And at tree level, this is it. Other massless particles can contribute. Whatever 3-point amplitudes are allowed at tree level, they can contribute. But you cannot have fermions because there is no 3-point amplitude with 2 bosons and 1 fermion. And you cannot have massive particles because they would not give you a singular limit. The pole that you would expect if a massive particle were exchanged here would be like 1 over s minus m squared, and it is not singular in the limit when the two particles approach each other. So this is the story at tree level. But once you start including loops, everything can now contribute. In particular, you can have massive particles circulating in the loop, which still produce a collinear divergence. You can have fermions circulating in the loop, and so on. But if you're just focusing on massive particles, there's an easy way to incorporate them. And this is by just assuming that you can integrate out the massive particles. And once you do that, it generates a bunch of new effective vertices. But like I told you, the collinear limits are only governed by the 3-point amplitudes. So I don't actually care about the higher point vertices they generate. I just care about what new 3-point amplitudes they generate. So I can go back to the example of Einstein gravity and consider that there is a massive fermion or a massive scalar in the theory. And what if I integrate out the massive fermion or scalar, I generate an effective R-cube interaction, amongst other things. And I've shown you this R-cube interaction here. I've written out the usual Einstein gravity 3-point amplitude just for comparison. Notice that it is different, but also it has its own Wilson coefficient now. And the subscripts on this Wilson coefficient essentially label the 3 helicities involved in the 3-point amplitude. So for the usual coupling, it's 2, 2, minus 2, it's 2 positive helicities and 1 negative helicity. And here it involves all positive helicities. So now this new 3-point amplitude modifies the OPE. This was the old term, which was from the red term that you see here, which is the contribution from Einstein gravity. And there's a new term here. Notice that it is the same order in Z12. It is still leading, but however, it's subleading in, it's of a different order in Z bar 12. And so we can account for massive particles by simply integrating out these, integrating them out and figuring out what 3-point amplitudes they generate. But you don't have to do this because we know all 3-point amplitudes involving massless particles are fixed by their helicity. So you can just write down all the 3-point amplitudes that you can in the theory, and that will give you all the terms in the OPE. This gives you all the most singular terms in the OPE. Now, once you exclude massless higher spins, there are only a finite number of terms that you can write down. And so the OPE actually has only a finite number of contributions at the most singular term. This should be contrasted with what happens if you actually integrate out the massive particle and you generate a lot of new vertices in the theory, but not all of them contribute because it's only the 3-point amplitudes that lead to a new singularity. And so these actually correspond to operators like R cube, F cube, R squared phi, etc. So, okay, are there any questions so far?
So for the exchange of just the gravitons, there are 3 possible terms in the OP: 2 parity, even 1 parity odd.
Yes, so there's the Einstein gravity term, there's the R cube term, and R squared phi term.
So
phi
I was
is
thinking just 3 gravitons, no phi. Isn't there also 3 in 4 dimensions? Isn't there also 3 graviton coupling that's parity odd? Maybe I misremember.
Well, there's only these. If you just have 3 gravitons, there's only these 2 you can write down.
That's
these
it?
2 amplitudes you can write down in 4 dimensions.
Certainly in higher dimension, in 5 and higher, there are 3 terms, right? There's Gauss-Bonnet, there's Riemann cube, and there's Einstein. I thought it was, but I'm maybe misremembering for him.
Right. So these are not in 1-to-1 correspondence with terms you can write down in the Lagrangian because it might happen that different contractions that you can write down actually give you the same 3-point amplitude when you put them on shell.
Yeah. No,
So this is just a statement at the level of amplitudes.
So in 5 and higher dimensions, at the level of graviton scattering, there are certainly 3 inequivalent 3-point graviton amplitudes. And you can write down
yes. So in higher dimensions, in 5 dimensions, it would have the massless particle would have 3 degrees of freedom. So I would expect more amplitudes there. But in 4 dimensions, it only has 2 degrees of freedom. So there are essentially these 2. If I'm looking at
my memory was that there was a parity odd coupling for 3 gravitons. Maybe I'm misremembering, but you're saying this is not right, 4 dimensions. If you're allowing for parity violation, is there one more coupling?
No, I think these are the only 2 couplings that you can write down.
Okay, thank you. Thank you.
Okay, so now I will switch topics a bit. We have all of these OPEs. What are they good for? You can ask, okay, I have these OPEs. Are they associative? And the usual way, one way of checking whether the OPEs are associative is to take the operator. You can mode expand the operator.
One more question. So, if I think of these OPE, I mean, these terms as giving terms in the OPE, right? These are the primary terms, I would imagine, right? So, what are the other primary terms, less singular ones? What would those correspond to?
Oh,
in general, conform field theory, you would have all sorts of terms, right?
Yes, so there's one family of terms that you can get. These are higher powers in Z bar. So that you can get just by demanding invariance under the SL2R right. And so that is fixed. But the terms which are non-singular in Z12, they're they're not known in general. They're known for certain classes of amplitudes, but it's not certain that it's not known how to write them in a universal way. So just from an amplitudes perspective, the non-singular terms would depend on which amplitude you're looking at, and there's no, we don't know any way in which, any universal way to describe them yet.
But okay, I mean, just even in the example, what kind of things, let's say from the bulk amplitude point of view, would give rise to such terms?
So the point is, this is just the subleading terms here cannot be written as something times a lower point amplitude. So there's no clean expression for them. It depends on which amplitude you're looking at.
I see. But sorry, I mean, from the OP point of view, it is always this form, right? The one in the bottom. You always expect that form from the OP.
The leading term, yes, but the subleading terms, I don't know what they are.
No. I mean, as an OPE, general OPE, you expect such a form only that two operators go to single operator, right?
Yes. Yes. But so there are some conjectures as to what the subleading terms could be. It's possible that they're related to two particle operators or weirder operators in the CCFT, but as of now, nobody has found a clean way of writing it.
And the origin of the subleading operators is from loops?
No, even just at tree level, if you take an amplitude which is not MHV and you expand in the collinear limit, there are subleading terms in the collinear limit which cannot be written as lower point amplitudes. So somehow these have to be reflected in the OPE, but we're not sure how to write it yet.
Sorry, but the leading term is like 1 over Z. So the subleading term is what kind of singularity does the sublead does in the tree level example?
It wouldn't be singular. It would be Z12 to the 0 or Z12 to positive powers.
Fine. Okay.
So these are something which there's no universal expression for them in terms of the amplitudes, but yeah.
Okay, thank you.
Okay. So you could ask whether these OPEs are associative, and the usual way in which you can check whether it is by taking the operator, performing a mode expansion in the Z bar variables, and computing the Jacobi identity of these modes. What we would want to do is to translate this into a statement about scattering amplitudes. So we want to understand what exactly associativity of the OPE means in terms of scattering amplitudes. And so to make this connection, we first notice that the commutator of two of these modes, this is usual CFT, textbook CFT, the commutator of two of these modes can be written as a residue integral of OZ1, O1, O2. And this integral essentially computes the residue as Z1 goes to Z2. And if you apply this formula to the rest of the commutators in this Jacobi identity, you can easily see that this Jacobi identity is essentially equal to this combination of residues acting on the correlator. So each of these terms involves two residue operations because each of these terms is a double commutator. And so this combination of residues must equal 0 if the Jacobi identity is satisfied. But at this point, you can note that this combination of residues has no mention of delta 1, delta 2 whatsoever. And so you can ask what happens if I, instead of asking that it acts on the celestial amplitude, I just make it act on the momentum space amplitude. Is the 0, or what if I demand it? What happens if I demand that it vanishes? And it turns out that this combination of residues has a pretty nice interpretation from the amplitudes perspective. And to see this, we can again go back to the collinear limit. Let's see what happens. When I take residue Z1 goes to Z2, again, this is the statement that amplitudes factorize on these poles. So in this particular case, it is literally the product of a 3-point amplitude times a lower point amplitude. And notice that I'm taking the holomorphic limit here, Z1 going to Z2. And as I told you before, the 3-point amplitudes are written either in terms of Z bars or in terms of Zs. But the specific residue I'm taking makes Z1 equal to Z2. So the amplitude that is left over here must be written in terms of the Z bar variables. And just for notation, I'm calling it anti-holomorphic. So it is literally the product of an anti-holomorphic 3-point amplitude and an n-1 point amplitude. And I've just reproduced the statement here that the 3-point amplitudes are completely fixed, but it's not important at the moment. So I can go on and take one more residue. So I took Z1 going to Z2, and that bubbled out this 3-point amplitude. A further residue, Z2 going to Z3, will bubble out another 3-point amplitude. And by the same logic, again, this has to be anti-holomorphic. And what you can actually show is that this specific combination of residues can be interpreted as gluing these two 3-point amplitudes in the S, T, and U channel. So the result of this combination of residues is this: it produces for me a 4-point amplitude here. But this is not the complete 4-point amplitude in the theory. This is the 4-point amplitude that is built only out of these anti-holomorphic vertices. And so the statement is that the product of this 4-point amplitude times this n-1 point amplitude must vanish. But because these other insertions could be arbitrary, it's sufficient to demand that this specific 4-point amplitude vanishes. Once again, I want to emphasize that this is not saying that every 4-point amplitude vanishes. It is just saying that every 4-point amplitude that you can construct only out of anti-holomorphic vertices needs to vanish. And there is actually a cleaner way of making this statement. This is rather technical, so it doesn't matter if you don't digest it completely, but these amplitudes are that can be built only out of holomorphic vertices are the ones which are constructible by these holomorphic all-line shift recursion relations. The only reason I'm telling you this is because there is an easy formula which tells you when these amplitudes are constructible, and this you just have to evaluate certain combinations, this sum over helicities and this dimension of coupling. If this sum is less than 0, then this amplitude is something you can evaluate by all-line shift. And if it is bigger than 0, then you cannot evaluate it by all-line shift. And it is precisely these amplitudes which can be constructed by all-line shift that have to vanish. So let's look at some examples. At 4 points, the single minus amplitude and MHV amplitude are not all-line shift constructible. This is just an example. And so these are not amplitudes that have to vanish in order for associativity to be satisfied. Okay, let's look at even simpler examples. There's pure gravity, and there's only one anti-holomorphic vertex, so there's nothing I can construct out of. There's nothing I can construct only out of this. So all OPEs are associative, and so Einstein gravity is fine. So, but let me go on to adding higher dimension operators. So I can add the R-cube vertex that I showed you before. So this is holomorphic because the sum of helicities is positive. This is also this is also anti-holomorphic because the sum of helicities is positive. But I can glue these together to build a 4-point amplitude, and this is the all plus amplitude. Now, the constraint that I showed you before demands that this must vanish in order for the associativity of the OPE to be satisfied. But straight away, you can see that there is no way I can make this vanish without just setting the R-cube coefficient to be 0. So this tells you that if I just insert, if I just introduce an R-cube coupling, this is not valid. So what you can do is introduce a third vertex, which is R squared phi. And so in this case, you can, in addition to the previous 4-point contribution to the 4-point amplitude, you have a new contribution which comes from exchanging the massless scalar. And the resulting amplitude looks like this. And now there is a non-trivial way of getting this to vanish, and you can get it to vanish by setting this combination of couplings to 0. Now this is determining the R-cube coupling in terms of this coupling of the in terms of the higher dimension coupling of the graviton to the scalar. Right.
Sorry, Akshay, I'm not able to, sorry, I cannot understand the conclusion. So let's say you didn't have this phi, and you just had this 4-point function with the red and the blue, and then you concluded that you had to set k2 to 0.
Yes.
What does this mean? What does it mean physically? What is the physical result you arrived at? That the Einstein gravity deformed with an R-cube coupling is an inconsistent theory?
Well, that depends on. So, given the OPE that you have, assuming that there are no other contributions to the OPE, this is telling you that just adding an R-cube term is not consistent with this OPE being associative. Now, there are a number of ways in which this can change. If there are additional contributions to the OPE that we don't know about, which are not related to the collinear limits of amplitudes for some reason, then this conclusion no longer holds. But otherwise, this is telling you that with the OPE that you have, if you just add R-cube to Einstein gravity, this is not consistent with the theory being associative, with the OPE being associative.
And is there a way to express this condition in the amplitude language?
Yes. So that was right. So in the amplitude language, this the constraint, the OPE associativity constraint, is essentially telling you that all the amplitudes that you can build out of these anti-holomorphic vertices have to vanish.
Yeah. But
so
why do they have to vanish? Without saying OP should be associated. Let's say I don't know anything about this CCFT.
No, so that's the, yeah, so there is no reason just from looking at amplitudes for asking these to vanish. These are a weird constraint. But this one thing I can say is that this feels like a bit of an integrability constraint. So if people have looked at simpler theories with like self-dual gravity or self-dual Yang-Mills, in which it is known that there is in which the theory is integrable. In this case, you have amplitudes vanishing, and this is somehow echoing the same spirit. It's asking certain, and because here you're only demanding the holomorphic OPE to be associative, it's asking that everything that you can, all 4-point amplitudes you can construct out of these holomorphic vertices vanish somehow.
If you took the heterotic string, suppose you take heterotic string theory on a torus, that presumably has an R-cube coupling. Would that be ruled out by this consideration?
No, because the heterotic string, so I'll talk about this later, but you can actually look at the graviton amplitudes in the string theory in 10 dimensions, and the 4 graviton amplitude actually vanishes. So if you have all plus helicities, that actually vanishes.
So it means including in the heterotic string.
Yes.
Okay. Yeah. Okay.
That's fine, but it still doesn't tell you what happens if you compactify the theory in some non-trivial way. It's possible that if you compactify it non-trivially, you can end up with amplitudes in 4D, which violate this criterion. But as I'll tell you later on, there are some compactifications or some ways to characterize the low energy effective theory that guarantee that all of these constraints are taken care of.
It's already interesting you say that at tree level, your constraint is met by string. That's non-trivial.
Sorry?
It's already non-trivial that your constraint is met at tree level, right? That didn't have to be, right?
Yes.
Okay, it's interesting.
So yeah, again, I want to point out that this is a kind of a mix of tree and loop, because I'm including these higher derivative couplings, which you should think of as coming from integrating out massive particles.
You could do that at tree level.
At tree level, though. I'm just classical.
Yes. Yes.
Yeah. Yeah. Yes, I do.
Okay, and so there's another amplitude that you can actually build only out of anti-holomorphic vertices within the theory of gravitons and scalars, and that is this amplitude with 3 gravitons and 1 scalar. And it turns out that for this to vanish, you have to set kappa 200 to be equal to the graviton coupling, but this is always satisfied because this is just the equivalence principle. It's telling me that the scalar couples to the graviton with the same strength as the graviton couples to itself. So is
there any connection between your condition and supersymmetry? In the sense that if you take a maximally supersymmetric theory, can you show that it's automatically satisfied?
Yes, so this is the end of my talk, but I'll tell you that it's sufficient that if you have n equals 1 supersymmetry, it seems to be the case that these conditions are satisfied. I don't have a deep understanding as to why, but this is just something we checked.
Well, I'm not able to understand where these constraints coming and why are they being satisfied by.
Sorry?
Not able to understand. I guess, I mean, from the CCFT point of view, it's clear, but it would be it would be nice to kind of understand it without extra structure. I mean, just standard scattering amplitude way. What is it that we are demanding? What is it that the standard constraints miss? I mean, associativity, I would have thought somehow related to crossing symmetry or something of the scattering. That's not what is happening. I guess this decomposition between holomorphic and anti-holomorphic is also important.
Yes. So I agree that it would be interesting, but I think part of the point here is there seems to be some tension between asking that the CCFT behaves in the way you expect a conformal field theory to behave and what you expect from scattering amplitudes. Like there's, as far as I know, there is no reason to expect Einstein gravity plus R cube to be sick in any way. So there's a priori no reason to expect that these specific amplitudes must vanish. But the CCFT seems to be telling you that they must. One reason, like I said, could be that the OPE is not complete, that you should modify the OPE somehow, and that modification will take care of these, and these constraints will no longer be imposed. And maybe the less optimistic conclusion would be that the validity of this holography scheme is limited, but that's something that's still under investigation. I don't know. I don't know what the outcome will be.
Thank you.
Okay, so the upshot is that not only are the couplings constrained, but there's also the spectrum must contain specific. There must be specific particles in the spectrum in order for this constraint to be satisfied. Okay, and these are all the constraints that I derived from including only massive particles in the loop. You could go further and ask what happens if I include the massless particles in the loop. And these splitting functions are also well known. It is known that these massless loops, the splitting function has two kinds of contribution. There is a factorizing and a non-factorizing. And the difference between them is essentially, sorry, how am I doing on time? Is this okay?
Yeah. How long do you think you would need?
Maybe 10 minutes.
Yeah, that should be fine. Yes, please go ahead.
Okay. Right. So the difference between these two kinds of splitting functions essentially is that non-factorizing arise because of infrared divergences, and the factorizing are just finite corrections. So I will focus on the finite correction, the factorizing piece, and I'll be brief here, but the point is the factorizing piece introduces double poles into the OPE, and these double poles also have a single pole underneath them because the resulting operator still depends on the coordinates. And you can show that this results in a non-universal correction to the OPE. And this non-universal correction makes the OPE non-associative again. And this has been shown by various people in various guises. People doing twisted theory and twisted holography have seen this as the failure of associativity of these chiral algebras for form factors in self-dual gravity, in self-dual Yang-Mills. So this is a new kind of problem. And in these earlier papers, they cured this by introducing a scalar with a quartic kinetic term. But of course, there is a simpler way of curing this, and this leads to what I told you about supersymmetry earlier. So this is something that we checked. Like I said, there was a specific set of 4-point going back to the constraints that we got from massive particles. There's a specific set of 4-point amplitudes in the theory that had to vanish. And what you can do is you can you start off with a theory with n = 1 supersymmetry. And there are supersymmetry ward identities which make some amplitudes vanish. And these are essentially derived in the following way, because each of these particles is either the top of the multiplet, the positive helicity graviton are at the top of the multiplet. So if I act on it with a supercharge, it vanishes. And so the only particle that the supercharge can act on is this gravitino, and that this must vanish if supersymmetry is satisfied. So it is in this way, the supersymmetry ward identities demand that certain classes of amplitudes vanish. And this is a non-perturbative result. It holds at all loops. And what you can check is that in this specific, in our specific examples, it cures all the problems. That all the amplitudes that we wanted to vanish. In particular, for Einstein gravity, for example, the all plus amplitude and the all 3 plus with one scalar, they vanish. And more generally, you can show that in a generic theory with bosons and fermions, with all having spins less than 2, all being, and if you have n = 1 supersymmetry, the ward identities are sufficient to ensure that all the bad amplitudes vanish. And moreover, another, maybe related, but maybe unrelated, another magic happens, and that is that all of these contributions, which introduce these non-universal corrections to the OPE, they're also guaranteed to vanish because the contributions from the bosons in the loop cancel out the contributions from the fermions. So I don't know why this happens, but somehow n = 1 supersymmetry is sufficient to make all of the problems go away. And
that
finally,
also answers my question about the heterotic string, right?
yes.
It doesn't vanish in the bosonic string. Is your condition met for graviton and bosonic string? No.
No, so the 4-point amplitude, so you can rule out theories easily. If the 4-point there are specific amplitudes in string theory which are compactification independent. These are the positive helicity graviton amplitudes. These are amplitudes which involve only gravitons. And some other amplitudes, but in the specific case of the bosonic string, you can compute the 4-graviton amplitude with all positive helicities, and this turns out to be 0. And so this will remain non-zero even if you compactify the theory down to 4D. And so this tells you that the bosonic string theory will never give you upon compactification will never give you an OPE which is associative. But there are compactifications of the heterotic string which could give you supersymmetric, which give you n = 1 supersymmetry, theories with n = 1 supersymmetry, and by what I showed you before, these are guaranteed to preserve, these are guaranteed to satisfy the constraints that I derived. And so, okay, I'll end here. I won't talk about the few remaining things. So what we've shown is that the associativity of the celestial OPE seems to be very restrictive. But at this point, I should mention that there was a recent paper showing that there are in giving some evidence that there are new contributions to the OPE, and these are contributions that possibly have the interpretation of being due to multi-particle states or two-particle operators, and these might introduce branch cuts into the OPE. And in this case, it is possible in principle for holomorphic and anti-holomorphic contributions to cancel out each other, and thereby it is possible that there is a scenario in which these constraints are not necessary, but this is still far from understood. Nevertheless, what this paper also showed was that if in cases where the Jacobi identity criterion that I showed you earlier is satisfied, this new term doesn't arise. So somehow there is this class of supersymmetric theories which have a simple OPE, and they satisfy this naive associativity condition. So I don't understand what the role of supersymmetry and associativity is or how they're linked. But okay, so I'll end here. Thank you.
Zoom audience, any questions? If not, how about here? So I guess you mentioned here on the last slide, but let me just say, would it be that these associativity conditions that you're imposing are related to supersymmetry in some way? I mean, maybe you're imposing supersymmetry in some guys. In that, I mean, what I mean is that does it necessarily rule out theories, or as a consistent theory, if your things are not satisfied, if our associative conditions are not satisfied, or does it just say that this theory cannot be supersymmetric?
I mean, at this point, I think it's too bold to claim that if these associativity conditions are not satisfied, there's something wrong with the theory.
Okay.
I mean, that's my opinion anyway. We have to wait to see what if there are other ways in which the associativity conditions can be satisfied. For example, as I said, there could be new contributions to the OPE which are somehow not visible from the scattering amplitude side, and that takes care of these conditions in a very non-trivial way. Yeah, at the moment, I don't have a good understanding of why supersymmetry somehow simplifies all of this, but it is definitely interesting, and yeah, it's something I will think about. But
thank you.
It's not clear to me why supersymmetry naturally gives you some theories which are simple in some way.
More questions? If not, let's thank Akshay again for wanting to talk.
Thank you.
Thanks, Akshay.
It's very nice, Akshay. Thank you.
Thank you. Yeah, I had a lot of fun. See you.
Bye.